Today's article is from upper diffraction due to a single slit. Last time we have seen how the Fresnel and from upper diffraction takes place. Here, a question can be asked: explain from upper single slit experiment to obtain diffraction pattern, obtain expression for first minima and first maxima. Just like in interference pattern, in diffraction also, the maximum and minimum intensity points are going to form. In interference pattern, the points of bright and dark intensities are going to form. Same way here, the points of minimum and maximum intensities are going to form. Now, this is just a derivation, and we have said that every derivation that can be classified into 4 points. First is diagram, second is construction, third is explanation, and the fourth is covering. So here, let us draw this diagram. Already I have been drawn this diagram to consume my time. See here, these are the plane wavefront or parallel rays of light. Now these parallel rays of light, they are falling on a slit. The width of slit, it is a small a. I have written here. Consider a slit AB of width a is illuminated, right? A small a is illuminated by a plane wavefront of wavelength lambda. Lambda is the wavelength of this incident light. Now, when this light is falling on the slit, what happens? Suppose that the screen is placed at a distance capital D from the slit. I have written over here. A screen is placed at a distance capital D from slit. Now, on this screen, we are going to obtain a diffraction pattern. Next, a convex lens Mn is placed close to slit. Nearby the slit, a convex lens is placed. The function of this lens, it is to obtain the points of maximum and minimum intensity on the screen. This lens, it is going to converge the rays at a particular point or at a single point. Next, and different rays converges. Rays of plane wavefront converges at point P0. See here, these are the incident rays. They are traveling parallel. Now, when they are falling on this lens, these rays, they are getting converged at point P0. Mind well, here the path difference, that is AP0 and BP0, or we can say that the distances AP0 and BP0, they are equal, and therefore the path difference between the rays coming at point P0 from point A and B, that is equal to 0. And as the path difference is equal to 0, therefore the point is maximum point, or point is a bright point. And when the bright point is going to form over here, this point, it is at the center, and hence it is called as a central bright point. This point P0, it is called as a central maximum point or a central bright point. Here, see here, what is the diffraction? The phenomenon of bending of light due to the sharp edges of the obstacle and its encroachment into its geometrical shadow is called as a diffraction. Here, the light is going to touch at these sharp edges, and because of the sharp edges, this light is going to bend. Suppose that theta is angle of bending. This theta, it is also called as angle of diffraction. Mind well, here in this direction, the light is going to bend. At the same time, the light is going to bend on this side also. Or we can say that in a circular form, if the slit is in a circular form, the light will get bent in a circular form. and it will form some minimum and maximum point around this point P0. Here we are interested to obtain the expression for path difference. Now, to obtain the expression for path difference, see here, these are suppose the three rays which are coming on diffracted from the slit. They are falling on the lanes and they are getting converged at point P. Now, draw a perpendicular from point A on this BC. C is the foot of this perpendicular. This theta is the angle made by the perpendicular with the slit. And of course, this angle, they are equal. Also, they are equal with this angle. Draw perpendicular from point A on BC. The point A is a midpoint. Here we have drawn this point, the perpendicular AC. This point K is a midpoint, and therefore we can say, or we can write this OK equal to half BC equal to lambda by 2. It means that if lambda is the wavelength of if the lambda is the wavelength of incident light, half of the wavelength it is getting diverted, or half of the wavelength that travels along this direction, half of the wavelength travels along this direction. Here lambda is the wavelength. Here the path difference is integral multiple of wavelength. But as half of the wavelength it is traveling in this direction, the converged rays that produces the path difference equal to half of the integral multiple of half of the wavelength. And therefore, further we are going to obtain the condition for minimum. Here the point is the maximum point. Here the point will be minimum point. Now from figure we write sin theta equal to BC upon AB. See here, this is perpendicular. This is sin this is angle theta. This is hypotenuse. In a right angle triangle, sin theta equal to BC upon AB. Therefore, this BC equal to AB sin theta, but this AB it is equal to A, that is the width of the slit. Next, therefore, see here, this BC is what? BC is the path difference between AP and BP. The rays which are traveling from A to P and B to P, the path difference it is equal to BC. Now, at point P0, already I haven't told you, path difference is equal to 0. Therefore, point P0 it is a right point. It is also called as a central maximum point. Now let us obtain the condition for first minimum. We have said here this point P is going to form. Suppose this point P is what distance away from this P0. Now this point P, it may be a bright point, it may be a dark point. And therefore, if lambda is the wavelength here, we have said that lambda by 2 wavelength is traveling in this direction and it produces the destructive interference. It produces the destructive interference, and therefore this point P it will be minimum point. It is first point beyond the central maximum point, and that's why it is called as a first minimum point. And therefore we will obtain condition for first minimum. See here, we are having this path difference. Path difference BC equal to A sin theta, and therefore this PD equal to A sin theta. Path difference, it is equal to A sin theta, that is equal to plus or minus n lambda. That is equal to A sin theta equal to plus or minus n lambda. Again, from figure or from this we write as theta is small, sin theta equal to theta, and therefore theta equal to L lambda upon A. What is this? This is the angular separation, or this is the angle made by the diffracted ray with its original position. Next, for a point, this point P to be minimum, we will obtain condition for first maximum. Now suppose that this point P is a maximum point, and therefore this path difference PD equal to A sin theta, that will be equal to plus or minus n plus half into lambda, plus or minus n plus half into lambda. Suppose this is equation number 1, this is equation number 2. As theta is small, sin theta equal to theta, and therefore we get this theta equal to plus or minus n plus half into lambda. So this is the condition for first minimum. This is the condition for first maximum. So these are the conditions we have obtained. So these are the conditions we write. These are conditions for first minimum and first maximum. So these are the conditions, and we have obtained the conditions for first minimum and first maximum. Now with this we will proceed to obtain we are interested in finding the distance of nth dark point and nth bright point. Let y and b distance of nth dark point. Now from figure, we write this theta n equal to or theta n d for dark point. The angular separation of n the dark point, it is equal to y n d upon capital D. Look at this. This is the y distance. Now suppose that this point P, it is a yn distance away from P0 point. Then, and this lens it is kept close to the slit, and therefore we write opposite side divided by adjacent side, that is equal to theta, tan of theta, opposite side divided by adjacent side. Tan theta n d equal to y n d upon capital D. Now, theta, as theta is very small, this tan theta n d equal to theta n d, that is equal to y n d upon D. This is suppose equation number 1, or this I'll write equation as A. Also, for first minimum, we are having this condition theta equal to n lambda upon A. We have theta n d equal to n lambda upon A. And therefore, this is equation suppose B. From A and B, we write y n d upon capital D equal to n lambda upon A, and therefore we write this y n d equal to n lambda into capital D upon A, which is equal to n into W. W is weight. W is weight. And y b d or y n b, it is a bright point, distance of bright point or nth bright. And therefore from figure we write for bright point we are having, or maximum point we are having this condition theta n b equal to plus or minus n plus half into lambda. This is suppose equation C. From equation A and C, we write, from this equation A and C, we write y n b equal to y n b equal to n lambda n plus half into lambda d upon small a, which is equal to n plus half into W, where this W is width of the, this W it is width of the central bright point and first minimum, central bright point and first maximum. From this we write width, it is equal to width of central bright. That is equal to 2W. That is nothing but 2 lambda D upon A. 2 lambda D upon A. Got this? So this way we can find the expression for central bright point. Mind well, here this point it is first minimum, this point it will be first minimum, and the distance between these 2 points, that is the width of central bright point. Width of central bright point. It means what? The central bright point, it will be spread between 2 first minimum. Between 2 first minimum.